Hello. This video is about field extensions and the notion of the degree. Before we talked about smallest possible fields called prime fields, and any field in the universe contains one of those. So let's look at the situation when one field sits inside another. This is called the extension of fields. This is the general way fields can be related. Again, that was mentioned in the previous video, but this is just simply because we're interested in unital homomorphisms, and so the zero homomorphism is not really an interesting thing anyway. And if we look at a homomorphism out of a field, it has to be, if it is non-zero, it has to be an embedding, because there are no possibilities for interesting kernels. Kernels are ideals and fields could not accommodate them. So this is a general relation between any two fields, and we are looking at a smaller field sitting inside a bigger field. And the first thing to observe, it's really a simple thing, but it's really a very powerful thing. So most of powerful things are simple in nature. This fact is that the larger field can be seen as a vector space over a smaller field. Simply because we have a multiplication in E, and part of this multiplication is multiplying with elements in F. So any element in E can be multiplied with any element in F, and then addition will be making this a vector space together with multiplication by scalars by elements of F. So that is a very simple observation which immediately allows for measuring in an interesting way the size of this extension. Because we have a measure of size of vector spaces, this is called a dimension. This is a number which counts how many basic elements we need to single out, how many elements we need to single out in E to express everything as a linear combination, and the smallest such is called a dimension. So this is a number of elements in any possible basis. It doesn't depend on the way we choose the system of generators. And we will assume, for this discussion, we will assume that this is finite. So that is called in field theory, called the case of finite extension. This dimension are traditionally denoted in a different way, in a way very close to group theory. The index of F in E, the order is reversed, and the index of F of subfield F in the field E is, by the definition, is this dimension. So the first example comes from a special class of extensions we discussed before, extensions where we attach just one single element, one single element on top of F. And the index, this dimension of the result of such attachment, is equal to the degree of the smallest possible polynomial for which alpha is a root. So P here is this minimal polynomial of alpha. The first fact about this concept, about this index, and it's really the only factor which we'll be using, is the following. Let's imagine a situation where we have two extensions connected this way. So the field F is contained in the field E, which is in its turn is contained in the larger field L. So suppose that we have this chain of extensions. and suppose that I will find it. Then we have the following relation between the indices. So the larger index, this index of f inside L, will be the product of two smaller indices, the index of E inside L and the index of F inside E. To verify this, all you need to do is to unpack the definitions of these two and compare it with what that number is supposed to count. So let's look at L. Let's write down this index. Let's look at L as a vector space over E, and this number, well, let's choose it to be n. So this number counts how many basic vectors we should have in any basis. So let's just choose a basis over E and just write some notations for basic vectors. Let's call them L1 up to all Ln, up to Ln. So that is a statement that the dimension of L as a vector space over E is n. While equivalently this statement that L is generated by this basis can be written in a formalic way. So any vector from this vector space L is uniquely writable as a linear combination of vectors Li. So some coefficients are in order here, xi I will call them. So these xi's are scalars for this vector space, so they are elements in E. Now let's call this number m and write the statement that the dimension of E as a vector space over F is m. So E is generated as a vector space over F by m vectors. Let's call them E1, En, all the way up to. And then, again, any vector from E is uniquely a linear combination of these vectors, of these elements of E, with coefficients in F. So any element xi we used in this combination, any scalar it was then, is an element in E, and so we can take it and write this unique combination, linear combination of ej's. I will use a different running index. And I will have now to invent a name for coefficients. Now they are elements of F. I will just simply call them xij. So these coefficients are now elements in F. So these are the two statements which really are the results of unpacking these two definitions. Let's combine them now. So we have L, an arbitrary element of our largest field, expanded first in this way, and then each of the coefficients is expanded further in this way, and these are the unique expansions. So let's combine them and write the result of substituting these sums inside this sum. So we'll have two sums. I'll combine them immediately. There will be two running indices. Now I'll probably not combine them immediately, but I'll just write the two sums together next to each other, and then I'll have the summand in these terms. I forgot all I. So now what I have is a unique presentation of any of arbitrary elements in L as a combination of some elements from L and then some coefficients in F. This is a statement that L has a basis as a vector space over F, and this basis is this collection of products, collection of these products. And I and J are running between N and M correspondingly, so the dimension is just the product of the N and M, hence the formula. So prove the formula, let's put it immediately to some use. The application of this formula will be to the collection of all algebraic numbers. Let me denote this collection, this subset of complex numbers, as rational numbers with this bar over, which will be really the generic notation for what is called the algebraic closure. So this is for today. This is the set of all algebraic numbers. By the definition, a complex number is algebraic if it is a root of a polynomial with rational coefficients. So let's immediately rewrite this definition into the statement on indices. So alpha is algebraic if and only if the corresponding extension is finite. And now you immediately can see how it is going to be used to prove something about this collection of algebraic numbers, namely this is a subfield. Hence it is, well, by the definition it is closed under addition, subtraction, multiplication and division. Surprisingly, division is the easiest statement. Addition and multiplication are more interesting. So the division part I'm leaving to you as an exercise. The addition and multiplication I will argue for using this little statement. So let's take two algebraic numbers, and what we need to show is that their sum and their product are also algebraic. So we have this characterization in terms of indices of what is to be algebraic. We will have to look at extensions of rational numbers by the sum and by the product of alpha and beta, and argue that they are finite degree. Instead, I will argue that the result of attaching both alpha and beta to rational numbers is of finite degree. So this is a different statement, but this is a better statement. It immediately will imply that the algebraic extension, that the extensions, field extensions by alpha plus beta and by alpha times beta are both finite because they are inside this extension. So if I take alpha plus beta, it will be inside this two-stage extension, and also the product extending rationals will also be a subfield of this. So if this is finite, then those two are finite automatically. Now, how can I see that this is finite? I'm going to write it as a two-stage extension. So I'm going to look at this as a two-stage extension. I'm going to write the resulting index, this index, as a product of two. So what is this two-stage extension? Well, it's a matter of choice. It's sort of symmetric in alpha and beta, so I could just have to choose which one comes first. And it's just the unpacking what this field is. It's a result of attaching alpha and beta, but I could do it in steps. I could attach alpha first, and then I could attach to the result of that beta. So that would be my extension. Where should I squeeze it in? I probably will squeeze in here. So the rational with alpha and beta attached can be seen as alpha attached first and beta attached after that. And that really gives me the chain of extensions like that. So first I will look at the result of alpha inside it, and then it obviously contains rational numbers. So looking at this chain, using this property, I will write my index as a product of two. It will be rational. I have to start with this first. So that will measure how much I enlarge my field by attaching beta. How much the dimension grows, the degrees increases, and here I will just be measuring the degree of this extension. And by the condition alpha is algebraic, so this is finite, and this is finite as well, because look what happens. So we're attaching beta to not just rational numbers, but to rational numbers with alpha already attached. So let me write this index here and compare it with the index of the extension by beta. By the condition that beta is algebraic, this is finite. So I have to argue that this is finite, but it has to be not larger than this, because what do we measure here? Effectively, according to this observation, we measure the degree of the smallest polynomial which has beta as its root, smallest polynomial with rational coefficients. So here we will be counting this degree, finding this degree of the smallest polynomial for which beta is a root with coefficients in the larger field. Of course, the original polynomial will still be true over this enlarged field, but what can happen is that over the larger field this polynomial will become reducible and will have even smaller polynomials. So this degree cannot be larger, it's always bounded. But the condition, this is finite, so this is finite, so these two are finite, so this is finite, we are done. And we have this statement that the collection of all algebraic numbers is a ring. Well, this is delegated to you to check that this is actually a field that in the inverse to any algebraic number is also algebraic. This is straightforward. You just have to find the polynomial which will have alpha inverse as its root. And you can find it by starting with a polynomial for which alpha is a root. So I will stop here. I will see you soon. Goodbye.